Okay, so let me share the screen. So starting with the new chapter, which is limits, fits, and tolerances. Now, we have known long that we can't produce any object with the same dimension n number of times. Most of the times, the objects which we are going to manufacture, they are going to be manufactured in the dimensions which are near to the one what we want. Okay. So there was a term, I think I had already taught it earlier, interchangeability. Anyone who can tell me what does this mean, interchangeability?
So that all the products or items are of a standard size and we can use anyone with for a different part as well. Like पेन का अगर हम लोग refill निकालेंगे तो हम लोग दूसरी refill उसमें use कर सकते हैं.
Yeah. So one thing that we can see is that because of interchangeability, we are able to do assembly properly. But how these dimensions are identified? How do we find out that with what? I mean, what is the range in which it is permissible? So, what is the range in which this assembly is permissible? For example, if I have to, there is a shaft, right? And there is a hole over here. So we got a shaft and a hole. Now this shaft has to be assembled in this hole over here. Now this could be larger, smaller, and that's what happens in the assembly also. So how do we ensure that whatever we are producing, because we can't produce in the same exact size, so how do we ensure while we are doing this manufacturing, we can achieve this assembly? So for that purpose, we have this concept of limits, fits, and tolerances. Okay, so there are several terms which will be used. So let me first talk about limits, fits, and tolerances individually. So what are limits? What are limits? From interchangeability point of view, we can define limits as two extreme permissible sizes. Two extreme permissible sizes of a part between which actual size is contained. So what is the important thing to understand is that these are the extreme permissible sizes. Now, what is the meaning of permissible size? Permissible from the point of view of assembly, that if your part varies between these two extremes, if the size of the part varies between these two extremes, it is good enough to be assembled. Okay, so we define that as limit. And then what is fit? So it is the kind of a relationship Fit exhibits a sort of a relationship between the mating parts. Between the parts being assembled. Okay. With respect to the difference on their sizes before assembly. So before assembly, it's not like we are going to bring parts together and check whether they'll be fitting with each other or not. No, it has to be done before. The fit has to be established before assembling. That is, the relationship between these two parts is that there is going to be a relative movement between the hole and the shaft, or it could be there's not going to be relative movement. There's going to be a tight fit between the hole and the shaft so that it does not move. Okay, so we give them several names. Anyone knows what name do we give to different type of fits?
Go and no go.
No, that's gauge. So fit is, you can say, we got interference fit, we got clearance fit, we got transition fit. Have you heard about this? Anyone? Okay. So it is the relationship between the parts being assembled. And then the third one is tolerance. So tolerance is defined as the total permissible variation of a size. Total permissible variation of a size. Of a size means, let's say I want to produce a shaft of 50 mm. Okay. Now 50 mm shaft is the size which I want to produce. So the size word over here indicates that 50 mm and how much permissible variation is allowed in that. So permissible variation uh, from the we call this as a basic size. Okay. So we will talk about them more. And then there is a term called clearance. So limits are generally an indication of it's sort of a range in which your part can vary. Fit is a sort of a relationship which tells the parts being assembled what is the relationship between them. Is there going to be a movement, or not going to be a movement, or sometimes there'll be movement and sometimes not. So that is fit, and the tolerance is the total permissible variation of a size. And then there is a term called clearance. So often these terms, while you are using, you should be clear when why are you using these terms. We will understand these terms with a figure also, but right now let's try to understand it uh, in words. So clearance is the distance between the adjacent surface of mating parts. Distance between the adjacent. I'm just checking whether I started the recording or not. Yeah. Distance between the adjacent surfaces of mating parts. Mating parts or parts being assembled, it's more or less same. So you can also say that how much the mating parts clear each other. That means what is the gap between them. Okay. So now let's see if we make a figure. So this is your hole and the shaft is here, let's say. This is your shaft. Okay, it has been assembled in this. So we can see that this gap which you see is called clearance. Okay, and fit over here is clearance fit because it can slide inside and outside the hole over here. So this is the fit is a clearance fit over here, and the tolerance would be that, let's say your basic size of the shaft is uh, 50 from here to here. This is 50. Okay, and this much it can vary. The size of the shaft can vary in this shaded region. So this shaded region is indicating your tolerance. Okay, and the limits you can see, this value, let's say, is 50.1, and this value, the above one is 50.5. So this is your these are the limits. Okay, now we go ahead and talk further.
So, sir, in this case, the tolerance would be 0.4.
Yeah. So there's a term called basic size. Why we are doing all this is because if you go to manufacturing, uh, you just can't go on producing like this. And while you're designing a product, you have to take care of the standards of the tolerances. Okay. Now, we will see that later, that how it becomes important when we are assembling, because multiple products being assembled, their tolerances gets added up. So while you're designing, you have to take care of the tolerance part also. Basic, or there's another term, nominal size. So it's based on which the dimensional deviations are given. So you can say this is the size we want to produce. And we apply the tolerances on this. I mean, plus minus, and this is basic. Basic means this is what I want. Okay. Uh,
So what will be the tolerance in the above example?
0.4. So how does it lead to interchangeability? Let's go there. Yeah. So this is the basic size which I have just introduced. Now we talk about tolerances first. So tolerance can be classified under 4 categories. You can have unilateral tolerance. You can have bilateral tolerance. Then you can have compound tolerance. And then you can have geometric tolerance. So let's talk about each of them one by one. So in the unilateral tolerance, the tolerance distribution is only on one side. So what do I mean distribution? See, as soon as I'm taking the word distribution, it refers to the kind of distribution, normal distribution, which we have done, like your the different sizes which will be produced, they'll be following a certain distribution. Okay, because multiple observations are there, they'll be distributed. That's why we are using the word tolerance distribution is only when your tolerance is distributed only one side of the basic size. For example, 40 if it's the basic size. So, and we in the superscript we indicate the tolerance over here. So the limits are indicated as superscript over here. You can see that they are all going in the positive direction. Okay, so you may be getting 40.01, 40.0. So these are the limits between which you will be getting your dimensions. And then it could be like this. I mean, we've already taken this. Let's say it could be negative also. Negative, and here it could be, we'll make it 1. Okay, so they are going, they are in distributed on one side of the basic size. So now you know that how can we define the bilateral tolerance? Yes, anyone? What would happen in the bilateral tolerance?
We would have both negative and positive tolerances.
Yeah, so they would be somewhat like this, 0.02 plus minus. They will be, they can be above and below. So if we, let's say, we have a basic size, I'll show it figuratively also here. So this is your, let's say, shaft. Okay, and your basic size is indicated by this line over here. This line is indicating basic size of 40. Okay, so if it is 40 minus if it is 40 minus 0.02, it will be somewhat like this. So this is going to be your clearance over here, and it could be plus also. So it is varying from negative to positive, above and below the basic size. Okay. So it is allowed to vary on both the sides. It can be other way also, other way in the sense it can be, it's not necessary that it is equally distributed on both the sides. It could be 0.02 and it could be minus 0.01 as well as a bilateral tolerance. Okay, then we talk about the compound tolerance. Now, compound tolerance, yeah.
So while defining the tolerance, we always define the lower value on the lower side.
Yeah. The lower value has to be written in the superscript. The lower value has to be written lower at the lower side, and then the upper side you have to write the upper limit.
Okay, sir.
And then we have the compound tolerance. So in the compound tolerance, what actually, I'll make a figure first. So let's say you have a figure like this. Okay. And this distance we are saying is R. Okay. And you can say this recess has to be manufactured. I mean, you have to produce it. This profile has to be produced. Okay, this is the cross section of that. So this angle could be if it is 60 degree, it could be plus minus 2 degrees. Okay, the tolerance is shown over here. Now, and also, let me remove this one first. This length is given. Also, there is going to be limits applied to this length over here. So correspondingly, this will be governed, and the value of this, let's say, is 20 degrees plus minus 0.1 degree. I hope you're understanding why degree is assigned to this dimension over here. So R is actually a compound. R will actually have a compound tolerance because it is dependent on these three dimensions. Okay, this is dependent on A, this is dependent on B, and this is dependent on C. So this is a resultant tolerance which you get. The tolerance on R is a resultant of A, B, and C. Are you getting it? So that's why it is called as a compound tolerance.
Sir, why dimension B is in degrees?
Okay, let's say I'll not complicate it. We make it a mm only. Okay, I'll not complicate your this thing right now. Okay, I mean 20. This is 40 and this is 20 and plus minus 0.1. Okay, so this is called compound tolerance, and this is very much common if you are doing assembly. Can you tell where do you see this kind of profile? Anyone? Can anyone tell?
Foundry.
Lathe machine.
Lathe machine, very right. On the rails, the rails on which your saddle moves, right? So you see this kind of profile, and assembly is required in that. You know that. So, and then we have the fourth type of tolerance, which is geometric tolerance. Now, geometric tolerance, it is having too much variety. Let's say this is your kind of a shaft. Okay. Now, this is cylindrical, and is it possible to make it 100% concentric? So there are some there'll be some variations in the form of the product which you see over here. So what variations can be there in the form? Variation in the geometric form. Can you tell me? This assembly will require what all things or to be looked into. Let's say even this is not an assembly, this is a solid object, okay, made by turning and on the lathe. So let me tell you the meaning of geometric form over here. So if you look at it, it has to be a perfect. So in the front view, if you look, there are two circles you will see. If you project it like this, you're going to see two circles, concentric circles, right? Now, there are two things, that is concentricity. Can we get a perfect concentricity? Say yes and no. I mean,
No, sir.
is it? No, it's not possible to get a perfect concentricity. Even I have not been able to make it over here. Besides concentricity, is it possible to have 100% circularity? They'll be elliptical to some extent, to a very minor extent maybe, but they'll be elliptical. Okay, slightly. And what else could be there? So concentricity is going to see whether these circles are aligned with the common center or not. Okay, and then circularity is going to see whether they are perfectly circular or not. Okay, so this is called sort of geometric tolerance. Now let me share my screen and I'll show a slide. Just a second, yeah. So what you see over here are various forms of geometric tolerances. So you can see over here, the first one is form tolerance. So you got form tolerance over here. And in the form tolerance, we talk about straightness, circularity, flatness, and cylindricity. So we probably not think about it. So cylindricity is also another form of geometric characteristic, because how perfectly it is a cylindrical object, because there is a possibility the lines may not be parallel. Your peripheral lines may not be parallel, so it can lead to loss of cylindricity, flatness, circularity, and your straightness. Similarly, you have orientation tolerance, that angularity, if there is an angle between the meeting parts, if there is a parallelism which is involved, and there is a perpendicularity. So, I mean, angularity, you can consider it to be a perpendicular. Both of these two are related with each other only. It's a special case. Angularity, special case is perpendicularity. And then you have position tolerance, where you talk about concentricity, symmetry, and any other position which may not be symmetrical. So we say that as a position. So again, you can say uh, concentricity is a special case of position. And then run out, where there is a circular run out and a total run out. Okay, so these are, I'll share this, you can read it later. So there are these are different types of tolerances which you see. Now I'll show some interesting video. Just a second. Geometrical tolerance. Let's play this video. Okay, before geometric tolerance, I would like to also show you another one, types of tolerances. Yeah.
Hello friends, today we will learn types of tolerance used in manufacturing process. Tolerance broadly classified into two categories: dimensional tolerance and geometrical tolerance. Geometrical tolerance we will discuss later in upcoming video. Now dimensional tolerance is classified into two categories, that is unilateral tolerance and bilateral tolerance. Now, in previous video, we have studied that the difference between upper limit and lower limit of subjective dimension of jaw is known as tolerance. And the zone between upper limit and lower limit is known as the tolerance zone. Third one is the actual size must lie in this tolerance zone. Now we have to study dimensional tolerance. The tolerance given to control the dimensional feature is known as dimensional tolerance. Dimensional feature may be length, width, height, diameter, etc. Unilateral tolerance means one-side tolerance. The tolerance zone always lie above zero line or below zero line in case of unilateral tolerance.
So zero line indicates your basic size. Okay.
That is one-side tolerance. Below zero line examples, case 1, here you can see zero line, lower limit, upper limit, and this is tolerance zone.
So this is the zero line, which is your basic size. Here the basic size is 50. So you can have a lower limit, okay, and the upper limit. So lower limit for a shaft, it will be reverse in hole, right? We talk about that later. So this is the lower limit of shaft, and this is the upper limit of shaft.
Now tolerance zone is touching zero line but below zero line. Now case 2, zero line, this is lower limit, upper limit, tolerance zone. Again you can see tolerance zone is below zero line and in this case not touching to the zero line. In case 1 for basic size 50, upper deviation is 0, and lower deviation is minus 0.060.
So upper deviation and lower deviation, what is indicating to is we will talk about that later.
This yellow patch showing lower deviation and this red line showing the upper deviation. Now as upper deviation is 0, hence this red line is matching to the 0 line. In case 2 for basic size 50, upper deviation is minus 0.070 and lower deviation is minus 0.110. Again here yellow patch showing lower deviation and red patch showing upper deviation. In both the cases, tolerance zone lies below zero line. It means negative deviation only. Unilateral tolerance above zero line example. Here you can see this is tolerance zone which is above zero line and touching to the zero line. For basic size 50, upper deviation is 40 micron and which is shown in tolerance zone. In case 2, the tolerance zone is also above zero line but not touching to the zero line.
So let me explain anyway, now that he's already talked a lot about the upper deviation. So what is deviation? It is the algebraic difference between the size and its corresponding basic size. Okay, size means you can say actual size and the basic size difference. Okay, and then you have upper deviation and lower deviation. So upper deviation is the algebraic difference between the maximum limit of size and the corresponding basic size. Okay, so when we'll be coming to the numericals, that time we will understand more. Right now, if I give too much information about deviation, it may not be very suitable. Okay, then let's say we talk about geometric tolerance. Well, let's try to understand. I'll not go further with this video. It's okay. It's just to represent that how our tolerance is placed across the zero line that was used over here. Now we talk about geometric tolerances.
We have studied dimensional tolerances and why those are required. Similarly, we have seen why geometrical tolerances are required. Now we are going for geometrical tolerances. It is defined into dimensional tolerances and controlled features. We will see how it is used to define the allowable variation in form and size of individual features, or to define allowable variation between features. Geometrical tolerances are classified in two categories.
Sir,
Independent.
Yeah.
so the video is not visible.
Okay. So just a second.
Of the surface of the dog, where all elements of the features depend on other features. Now we will see one of
Sir,
the
please turn off your
independent
mic
geometrical
because the
tolerances.
voice is echoing.
Should I mute my mic?
Yes, sir.
That is straightness. Straightness is the condition of surface or axis where all elements of it are in a straight line within specified tolerance zone. Suppose we have to control straightness feature of top
Was it fine now? I've just paused it to check
Yes,
whether
sir,
it.
it was better.
Okay. So I'll not be able to hear you guys. Just let this video complete.
surface of this job, then we will have to mention it using feature control frame, where in this feature control frame, in first block, straight line is indicating the feature symbol. This feature symbol is for straightness, and this 0.02 is the straightness tolerance zone. So this straightness tolerance zone is defined by two parallel lines which are 0.02 distance apart from each other. Now this top surface which we have to control for straightness may lie like this or like this. But in both the condition, it is within the specified tolerance zone in between these two parallel lines. So it is acceptable. Now let's consider another example. In this time, we are applying straightness condition for axis of the shaft. So it is saying that this axis should be straight within this specified tolerance zone. So for this purpose again, it will be defined by two parallel lines which are 0.02 distance apart from each other. So once again, it may be like this, but as it is in between these two parallel lines, so it is acceptable. Or it may be like this, or you can say, let's see here separately, in between these two parallel lines which are 0.002 distance apart, this axis may lie like this, or say like this. In all these cases, it is in between these two parallel lines, means in the specified tolerance zone, so it is acceptable. Now we will see how geometric tolerance is defining two dimensional. Suppose this is a job, 12 is width and this is height, 10 plus minus 0.05. This is the dimensional tolerance. And we have to control upper surface for straightness. So in this first block, this symbol of geometrical feature, straightness, and this is the geometrical tolerance, specified tolerance. And this complete block is known as feature control frame. So according to dimensional tolerance, lower limit will be 9.950 and upper limit will be 10.050. So this is the dimensional tolerance zone, which is 0.10. But according to geometrical tolerance zone, it will be like this, which is 0.02 distance apart to parallel lines. Let's see separately. Now this is dimensional tolerance, which is 0.100. So according to dimensional tolerance, if this surface is manufactured like this diagonally, it is acceptable. This is also acceptable. But geometrical tolerance is 0.02. So according to geometrical tolerance, it is not acceptable. Now observe the lines. These lines are more flat, means more straight than previous line. You can. So geometrical tolerance is controlling the geometric feature, means straightness. Now, in this dimensional tolerance zone, geometrical tolerance zone may shift anywhere from top to bottom. Wherever it is manufactured, from that position, it will control the geometrical.
So one thing that you would have observed by now is that the geometrical tolerances are complex in nature. Am I audible?
Yes, sir.
And the dimensional tolerance, difference between the dimensional and geometrical tolerance is also evident in this. We will not be focusing more on geometrical tolerances in this course, but just to get you an idea of geometrical tolerance, this video was shown. Okay. Now, there are, while we are talking about tolerances, now we have understood that with the compound tolerance, it becomes difficult to apply it, and the geometrical tolerances are, you can say, relevant when you are having lot of assemblies which are with angular with respect to each other, or they have some positional issues. If the and generally that's the case, it's not always going to be a straight lines. Okay, so we go ahead and talk about metal conditions. So maximum and minimum metal conditions. Let's talk about that. Maximum.
So could you please share your screen?
Okay, that's maximum and minimum metal conditions. So if let's say we've got a dimension and the tolerance is like this, okay, and let's say if this is a shaft, this is the basic representing basic size, and this, let's say this is the tolerance zone of bit exaggerated, but then this is 40, 40.05 and 39.95. Okay, and this is your tolerance zone. So can you tell me what is the maximum metal condition for a shaft? What will be the maximum metal condition? Means the condition in which the shaft is going to have maximum metal.
40.05.
Yes.
The
So,
upper limit.
yeah. So for a shaft, the maximum metal condition is the upper limit, or upper tolerance limit, you can say. We call it as maximum metal condition or maximum metal limit, MML. So this is your MML, maximum metal limit, and lower metal limit is LML, that is for 39.95. If it's a hole, if this dimension which we have written over here is for a hole, what will be the maximum metal limit?
Lower tolerance.
If it's a hole like this, okay, let's say this is your basic size, and this is your tolerance zone, basic size of 40. So the upper limit of hole will be 40.05 and lower limit of hole will be 39.95. So maximum metal limit for hole will be when the hole is of the smallest size, or when the hole will be of maximum size.
Hole is of
Smallest.
smallest.
smallest, right? So maximum metal limit is 39.95 for hole, and lower metal limit for hole is 40.05. So for a hole and a shaft, these conditions get reversed. So why we were talking about maximum metal limit and lower metal limit? Because many of the terminology which we are going to see later is defined in terms of metal limits and not in terms of the upper and the lower limit. We always say maximum metal limit or the lower metal limit. Okay. So the relationship between the two mating parts that are to be assembled with respect to difference in their dimensions before assembly, we call that as a fit. And are you also listening to this? I mean, is there a disturbance coming?
Yes, sir.
Actually, there's a drilling or something going on in the workshop. So that's why so much disturbance. Anyway, I can't help it much. Maybe I can use the inside room from next class. I'll be taking the inside room. So we have three types of fits. Types of fits. I'll just introduce them today, and we will start with them in the next class. So first type, second type, and the third type. So first type of fit is a clearance fit. Clearance fit. The second type of fit is an interference fit. And the third type is transition fit. Okay, so we will talk about these three types of fits later. I'm also sharing the link for the attendance sheet. So let me just recap what we have done today. So we were talking about limits, fits, and tolerances, and they are largely based on the concept of interchangeability. That's why this topic has come into picture. Then there are four basic terms which we should be, or basically three, and then the clearance is a resultant of that. So limits, fits, and tolerances, there are three terms which we were interested in talking about. And limits indicate the two extreme permissible sizes. Fit indicates the relationship between the mating parts or the parts being assembled. Tolerance indicates the total permissible variation of a size. And clearance is the distance between the adjacent surfaces of mating parts. Then you can say that we understood the term basic size, nominal size. That is the size which we want to produce. Types of tolerances we understood: unilateral, bilateral, compound, and geometric. Geometric, we saw a video that how your dimensional tolerances are different from the geometric tolerances. And then we talked about maximum and minimum metal conditions for hole and a shaft, which are reversed to each other. And then we talked about the types of fits. Okay, so do you have any doubts? I'll share the attendance sheet now in the WhatsApp group. I'll be sending the attendance sheet. If you have any doubts, you can ask me.